Light is the essence of optical microscopy. But to understand light, you have to understand nano. What is a nanometer in terms of objects that we can relate to? Because light itself has a dimension in the visible of approximately 500 nanometers. So here is a scale of different materials that we could relate to that are in the scale of nanometers. For example, a water molecule is only 0.1 nanometer. That means 1 angstrom. A hydrogen atom is 0.5 angstroms. A water molecule is 2 hydrogen atoms and an oxygen. There are other molecules that we may have heard of, especially in this era of COVID-19, and that is antibodies. Antibodies are closer to the several nanometer regime. And then there are viruses. Viruses are about 100 nanometers. And these viruses that are 100 nanometers or so, okay, are a general dimension of viruses. You can have viruses as large as a quarter of a micron, which is 250 nanometers. And the COVID-19 is a virus with 120 nanometer dimension. Bacteria, which you can see in a regular optical microscope, have a dimension of 1,000 nanometers. That means that it's twice the size of a wave of light, which is 500 nanometers. And then there are cells. The smallest cell is the red blood cell, and the red blood cell is 7 microns in dimension. And then there is a period that you would put on your paper, and that is close to 1,000,000 nanometers. A useful comparison is that a tennis ball, which is 100 million nanometers, okay, is to a water molecule like a tennis ball is to the Earth itself. So a wavelength of light is 500 nanometers. That is in the middle of this spectrum that you see over here. And it's very close to what the sun's emission is like. You can have longer wavelengths, and this is the radio frequency wavelengths, microwave, infrared, and in this regime are what are called terahertz wavelengths. And then there are very short wavelengths which extend into the gamma ray that come from the nucleus of atoms, the X-rays that are available for imaging inside the body with destruction, of course, etc. Now, the general criterion is that you can only image these objects at a level of half a wavelength in an optical microscope. So a bacteria, which is 1,000 nanometers, would in fact be clearly able to be seen and imaged in an optical microscope somewhat. These criteria were established by Abbey in 1873 and Raleigh at the end of the 1800s. And in the Raleigh criterion, if you take 2 points of light and you want to separate them, as I said, you could resolve a bacterium readily because 1 point of light would come from one end of the bacterium, the other from another end, let us say, and you would be able to resolve 1,000 nanometers. But as you get closer and closer, these 2 points of light overlap in terms of their distribution of light as they come off the object you're trying to image. And as a result of that, the criterion of Rayleigh is that you have to have a peak to valley in the middle of this overlap that is 20%, and therefore this would be a resolvable item with optical microscopy. And this is the valley, and this is the peak that we are speaking about. If the object is, let us say, a virus, then the 2 points from the 2 ends of the virus, let's say the COVID-19 120 nanometer virus, would be too close to each other to be able to actually image them. And the 2 lobes that you see over here would overlap, and it would be unresolvable in an optical microscope, and so one would have to go to an electron microscope. So the world of optical imaging, as it stands with a standard optical microscope, is that you have 500 nanometers in X and Y. You have much worse in Z. You can do absorption, you can do fluorescence, and the whole imaging operation is parallel, which is really one of the exciting things about optical microscopy with a lens. But there is no super resolution, and there is no direct phase that is obtained. This means you don't get any 3D structure. You get an image which is 2D, okay? You just see, you don't know what the 3D depth of that image is. There is no 3D structure.